Hello everyone. In this video, we're going to be talking about integration, okay? Integration of the inverse trig functions. Okay, the integration of inverse trig functions. Okay? And the integration part is quite important. And I mean important, I mean like not just quite important, really, really important, okay? Because they let us integrate simpler functions, okay? So previously, like functions that previously could not be integrated, okay, into functions that can be integrated, okay? So if we couldn't find the integral of 1 over 1 plus x squared, okay? And that is because dx, that's because we couldn't do a U-substitution here, okay? There's no, if we let u equals x squared plus 1, there was no 2x, okay? So we couldn't take this integral, but turns out we can now, okay? Because since integration is the opposite of differentiation, you could say that the integral 1 over 1 plus x squared is the arctangent of x plus c. In fact, you can say this with many of the inverse trig functions, okay? The integral of this equals arc sine of x plus c. And the integral of 1 over x times the square root of x squared minus 1 is equal to the arcsecant of x plus c. Where are the other three? Well, if you remember, the derivatives of the other three were just negatives of them, okay? They were just negatives. So you really don't need to care about them, because if we just took the integral of this, that's the same as the integral of this. Okay, so we don't even need our cotangent because we just plot the negative sign. So this expression is utterly worthless. So you literally only need to memorize 3 rules: arctangent, arcsine, and arcsecant. Okay? And with these integration rules, the capacity of which you can integrate is a lot better. Okay? So let's do a couple of practice problems, okay? Let's do a couple of these practice problems. So let's say you want to integrate, okay, let's say you want to integrate, let's say you want to find a region, the area of a region. Okay, so what is the area of the region okay, what is the area of the region under under f of x equals 1 over 1 plus x squared from x equals -1 to 1, okay? So the graph is basically looks like this. Okay, so we just want to find the area of this red region I'm highlighting here. So what's the area of this red region? Well, this one's an easy one, okay? Because we're just taking the integral from -1 to 1 of 1 over 1 plus x squared. So that is just the arctangent of x from 1 to -1. So what's the arctangent of 1? What angle has a tangent of 1? Well, that's pi over 4. So pi over 4, okay, minus negative pi over 4. Because remember, arctangent is only defined on the interval negative pi over 2 to pi over 2. So you can't use 5 pi over 4, or not 5 pi over 4, 7 pi over 4 in this case, okay, or 3 pi over 4. You can't use that since it's not in the domain. So you have to use negative pi over 4. And you get an answer of pi over 2. Pi over 2. And that is the area of this red region, which seems surprising, kind of, because this function, okay, does not have any trig functions in it. However, the area results in a pi. That's just because of the integration rule, okay? Now, usually the problems are not this easy, okay? The problems are usually never this easy. So let's do this one, okay? Why not? Why don't we do the function, the integral, indefinite integral of e to the 2x over 4 plus e to the 4x dx, okay? So what do you do in this situation? Well, why don't we do a U-substitution? Okay, if we do a U-substitution, everything should be relatively fine. Okay, so notice that 4 equals 2 squared. Okay, let's write everything in terms of squares. 2 squared plus e to the 2x squared. Now you might now see where you can fit in this integration rule. Okay, you might see where you can fit in the integration rule. Because let u equals e to the 2x. Okay, so du, should put dx over here. du should be equal to 2e to the 2x dx. So we just need to introduce 1/2. Okay, and then we have 1 over 2 squared plus u squared du. Okay, so what is this integral? Okay, what is this integral? Well, this integral is equal to 1/2. Okay, this integral is equal to 1/2 times 1/2 arc tangent, okay, of u over 2 plus c. So 1/4 arc tangent of e to the 2x over 2 plus c. Okay? So the more detailed integration rules, okay? So where did I get this 1 over 2 from? Where did I get this 1 over 2 from? Well, if you rearrange it algebraically, okay? If you rearrange algebraically, then you get these more detailed integration rules. So I'm going to rewrite the integration rules, but instead of 1, I'm just going to put a constant a squared. So the integral of a squared minus u squared, not u squared, still in that u substitution mode, a squared minus x squared dx, that is equal to the arc sine of x minus a. So x over a plus c. Okay, the integral of 1 over x times the square root of x squared minus a squared, where a is any positive constant, is equal to 1 over a times the arc secant of x over a plus c. And the integral of 1 over a squared plus x squared dx is equal to 1 over a times the arctangent of x over a plus c. So you can derive all of these algebraically. However, it is best you memorize these full forms of the trig functions, of the inverse trig functions. Okay, now we have problems like this, and let's do another one. Okay, you also have problems like this. So we want to find the integral of x plus 2 over the square root of 4 minus x squared dx. So what is this integral? Well, you can try to replace x squared. Okay, you can try to replace x squared but make u equals 4 minus x squared, and you get negative 2x. However, you have an x plus 2, so you have an extra 2 over there. So we can't really use a u substitution in this case. So why don't we split apart this function into two integrals? The first integral will look like this, okay? And the second integral will look like this. Okay, it's just the properties of integration. And now using this definition, we can easily integrate because now we have a lone x, not an x plus 2, we have a lone x on the top of the left integral. So we can easily use a u substitution. Okay, so we have negative 1/2 times u to the negative 1/2 power. Yes? du. Plus 2 times the integral of 1 over the square root of 4 minus x squared dx. Okay? Now what do we get in return? Okay? We get 2 times u to the 1/2 power. Yes, we have 2 times u to the 1/2 power. So we have negative 1/2 times 2 times u. What's u? u is 4 minus x squared. To the 1/2 power, so these two cancel. Plus 2 times arc sine, it's an arc sine function, x over 2 plus c. Okay? And now we get our answer, 2 arc sine of x over 2 minus the square root of 4 minus x squared plus c. This is our integral. Okay? Now, we can do one more. Okay, why don't we do one more? So this one is a special one because the integral is hidden quite well. Okay? So why don't we find the integral of 1 over x squared minus 4x plus 7 dx. Now you can't split apart the denominator, okay? So you seem to be stuck, okay? But since we learned the inverse trig rules, why don't we try to get in some form of a square, okay? So what do I mean by some form of a square? Why don't we establish this lower polynomial, the quadratic function on the bottom, as a sum of squares? Okay, since we can't obviously fit in a square root. So this is where we go back to algebra and complete the square. Okay, or just separate squares from each other. Okay, so this equals x minus 2 squared plus 3. So that serves as a good starting point because the x is now in a squared expression. Plus 3 dx. Okay? Now, you might not realize it, but 3 is also a square. Not a perfect square, but it is the square of root 3. So now it fits our arctangent rule. Okay, it fits our arctangent rule. So we can rewrite this as 1 over root 3 plus, not plus, times arctangent of x minus 2 over root 3 plus c. So you can do what is known as completing the square, okay, and separate squared expressions from one another. Okay, so that you can fit it into one of the integration rules that we know. Okay, so this integral is this crazy looking expression. Okay, so with the conclusion of inverse trig functions, you can now take the derivative of any function, any single function, with the rules that we know, product rule, quotient rule, and all the trig rules and all the other rules. However, you can't integrate every function. Okay, so we expanded the base of which we can integrate, but we still can't really integrate every single function. Okay, however, it serves as a good launching point. And in the next couple of videos, okay, we're going to be learning about types and techniques of integration. Thanks for watching. If you have any questions, please comment below, like this video, and subscribe so that we can make more great videos such as this one.